Friends, good morning. Today I am going to deal with the multiple sequence alignment. I am not going to discuss the entire algorithm of multiple sequence alignment, shortly termed as MSA. A very few algorithms exclusively CLUSTAL W will be covered in this lecture. What is the goal of a multiple sequence alignment? Usually, multiple sequence alignment means equal to 3 or greater than 3 number of sequences we want to cluster. So you want to cluster at least 3 sequences or more than 3 sequences, then automatically that particular alignment is actually termed as multiple sequence alignment. So what should be the goal of multiple sequence alignment? In order to create the best overall alignment of a family of sequences, you may be in a position to cluster 10 sequences or 20 sequences or whatever it may be. So you want to have a best possible overall cluster of sequences. That is your goal. So what is the ideal approach? Ideal approach, say for example, k is equal to 5. That means 5 sequences you want to cluster. K is equal to 10. That means 10 sequences you want to cluster. So you will, if you try to cluster all the sequences at a time, all 5 sequences at a time, or all 10 sequences at a time. So that is ideal approach. What is shortcut approach? Instead of aligning all 5 sequences or 10 sequences at a time, you convert 5 sequences into pairwise or 10 sequences into pairwise. So that is actually shortcut approach. For 5 sequences, you want to create a pair. Sequence 1 and 2 is a pair. 1 and 3 is a pair. 1 and 4 is a pair. 1 and 5 is a pair. So like that, 5 sequences you convert into different pairs. For each pair, you calculate some score, and then progressively you add the next sequences. So this is actually shortcut approach. Ideal approach means all 5 sequences at a time will be clustered. So this is very difficult. So anyway, ideal approach is computationally highly intensive. Time consumption will be more. That is not ideal again. So we are not going for any ideal approach. Always multiple sequence alignment follows a kind of shortcut approach. What is the application scope of multiple sequence alignment? You want to characterize a protein families. That is impossible with the help of pairwise alignments. Using Needleman-Wunsch and Smith-Waterman, you can align sequences only pairwise. Out of that, you can comment about only identity or similarity, something like that. You can comment about homologous or orthologous or xenologous. Only this much information can be inferred with the help of pairwise. Whereas if you want to characterize a particular unknown protein, that is, to which family it fits to, whether the purified new novel protein belongs to an enzyme exactly, or a transport protein, or a receptor, or a signaling protein, or it is a simple peptide. So how to characterize based upon functionality, that is possible only with the help of multiple sequence alignment. So one application is to characterize protein families. Second application is you want to find consensus sequences, consensus characters, conserved characters. So how to find conserved characters? So conserved characters can be found only with the help of multiple sequence alignment. That is, for example, you have clustered 5 sequences. Position number 10, which character is retained? Position number 10, whether the expected character is retained or not, and any gap has been included. So presence of or retainment of conserved characters, characters which are very, very sensitive against mutation, that can be found with the help of only again multiple sequence alignment. The third thing is with the help of this multiple sequence alignment, you can comment about or you can predict about whether the protein belongs to a secondary or tertiary structure based upon the presence of characters, distribution of the characters. You can observe and then you can comment whether the protein belongs to secondary or tertiary. And finally, after doing multiple sequence alignment, you can extend to phylogenetic analysis. You can construct a phylogenetic tree. Based upon phylogenetic tree, you can infer the evolutionary history of the selected species, as well as the neighborhoodship or similarity existing between these species can be also commented. So 3 to 4 broad applications to characterize the protein families, to find the conserved characters, to predict secondary and protein structures, finally to predict a phylogenetic tree and to comment about the evolutionary history. For all these things, multiple sequence alignment play a major role. Now this is an example of treaty output which I got from CLUSTAL OMEGA, which is hosted by European Bioinformatics Institute. So here you can see each and every character, based upon properties, the characters were given some colors. So here you can see methionine, alanine, tryptophan. Here you can see histidine, so different colors, right? And this is a box shade output. Finally, we will try to do some simple practical exercise. We will try to cluster multiple sequences. We will try to create this box shade output from a server. So box shade output, the purpose of this box shade output is to highlight the conserved characters. Now here you can see, so M, A. Now here you can see PLL is not highlighted. Only conserved characters will be highlighted. M, A. Now here you can see Q, H, L, C. So very simple. Box shade is exhibiting the output in a very pretty way. So I want to exhibit, I want to show, I want to pinpoint the presence of conserved characters. So that is impossible over here. So it's very difficult. Now here you can see a conserved character, Y, but it's very difficult for me to find where conserved characters are distributed. So this output will give you only the multiple alignment, but it will not highlight the conserved characters. That can be done by another method, that is box shade method. So this is a pretty example box shade method which highlights the conserved characters you can identify. So what is the simple algorithm? Just you split multiple sequences into pairwise, that is pairwise clusters, right? For each pairwise, you calculate some score. And then finally, you predict a phylogenetic tree. You compare the pairwise scores, similarity scores, and then you compare that the leaves which are distributed in the phylogenetic tree. If both are same, that will be the output, right? So you can see different methods. One is dynamic programming, progressive alignment, iterative, and even we can go for statistical modeling. But for today's lecture, I am going to focus only progressive alignment. Again, we are not using dynamic programming. It is highly computationally intensive. Time consumption will be very high. So most of the scientific community exploit CLUSTAL W, which is a classical example for progressive global alignment. Remember, full form for CLUSTAL W is cluster all based upon some weight. CLUSTAL W, it is a classical example for global multiple sequence alignment. So 4 methods are available, but still for today's lecture, I'm going to explain only about progressive alignment by taking CLUSTAL W as an example. Okay. So here you can see what is progressive alignment. It's nothing but a kind of a greedy algorithm which will select the similar pairs, which will identify the similar pairs, and after identification of similar pairs, initially one by one sequences will be added. Suppose there are 5 sequences. 5 sequences will be converted, will be first splitted into pairs. As I said earlier, 1, 2, 1, 3, 1, 4, blah, blah, like that. And for each pair, the score will be calculated by using some dynamic programming approach. After that, if you find, say, 1 and 3, this pair is the highest similar pair. 1 and 3 first clustered. After this, the left Left out sequences are 2, 4 and 5. Which sequences should be added to this 1, 3 pair? Either 4 to be added or 5 to be added. That we have to decide. So assume 1 and 3 is the closest pair. Left out sequences 2, 4 and 5. Now for this 1 and 3, which sequence should be added to this pair? Either 2 or 4 or 5. That will be decided purely by placing the gap. So identification of gap, minimal gap, if a sequence is going to be added, so that will be added to the existing 1, 3, right? So it's a kind of greedy algorithm. So now you can see here, it's a very simple computational approach. Say there are say 5 sequences, 4 sequences, right? So now here you see first the sequences will be converted into a possible pair like this. Uh, sorry. So 1 and 3, 1 and 2, 1 and 4, 2 and 3, 2 and 4, 3 and 4. So all 4 sequences will not be clustered at a time. 4 sequences will be splitted into 6 different pairs. Use formula n into n minus 1 by 2. So n is equal to total number of sequences. So here there are 4 sequences, right? So 4 into 4 minus 1 by 2. So which is equal to 6 pairs. So now you can see 6 pairs was projected here. So first we will calculate the pairwise score. Now you see this is the first step in the CLUSTAL W algorithm of multiple sequence alignment. So the score 1 and 2 alignment score, 1 and 3 alignment score, or 2 and 4 alignment score. For each alignment, pairwise alignment, the score will be calculated by using a dynamic programming approach. As I said earlier, this is a global multiple sequence alignment. So a global alignment algorithm should be implemented over here. So the best choice is Needleman-Wunsch algorithm. You can use conventional Needleman-Wunsch algorithm, or you can use an enhanced Needleman-Wunsch algorithm. A better enhanced NW algorithm can be used over here. So based upon the alignment, you can calculate the score for each pair, right? Because global alignment uses 3 different variables. It uses match, mismatch, and indel. So once alignment is over, you can calculate the overall alignment score. So for each pairs 1 and 2, there will be an overall alignment score. 2, 4, there will be an overall alignment score. For each pair, there will be an overall alignment score. You pick which pair contains highest numerical, right? Highest numerical. That could be, for example, out of these pair, assume 2 and 4. 2 and 4 contains the optimal value. The overall score for 2 and 4 is plus 5, right? For rest of the pairs, the score is below plus 5. 2 and 4 score is plus 5. The rest of the pair, 1 and 2 or 1 and 3 or 1 and 4, their score is lesser than plus 5. So 2 and 5 should be considered as the most similar pair, most similar sequence, right? So that is the first part of the algorithm, right? So now here you can see, assume here 1 and 2. So this was considered as the best pair, right? Now I have added 1 and 2 over here. Now you can see this 3 and 4 seems to be very close. So initially I have clustered 1 and 2, 3 and 4 separately. After finding 1 and 2 is the most similar pair, to this 1 and 2 pair, which sequence should be added? Either 3 or 4. That I have to decide. So now here you see, by using, if you go for this third sequence, you go for a third sequence, that is LQS. By incorporating one gap, you can add to the existing pair. Whereas if you go for the fourth sequence, L, S, and F, you have to incorporate 2 gaps. Please remember, number of gaps allotted is directly proportional to divergence. You are clustering the sequence by using similarity, not based upon divergence. So when you try to accommodate more number of gaps, that shows that that particular sequence and that particular species is highly diverging from the existing pairs, from the existing species. So in that case, where the third sequence or the third species, you see, by incorporating just one gap, you can add to the existing 1 and 2. So the wisest decision is progressively I have to add sequence number 3 to the existing pair 1 and 2, not the sequence 4. I should not add sequence 4 to 1 and 2. Right? The alignment nature should not be like this. 1, 2, 4. It should not be like this. It should be 1, 2, and 3, because in the third sequence you can progressively add to sequence pair 1 and 2 by placing only one gap. So accommodation of gap play a major role in this kind of progressive multiple sequence alignment, right? So see the algorithm. You break the sequences into pairwise, calculate the pairwise alignment by implementing appropriate dynamic programming approach. Now you construct the alignment. Now here we have constructed the alignment. The multiple sequence alignment says 1, 2, 3, 4. That means 1 and 2 sequences are very, very close to this 1 and 2. Which sequence is very close? 3 or 4? 3 is very close. And then 4. So I will add third sequence progressively and then fourth sequence. This is based upon the first step. Now I want to ensure whether the alignment what I have created or what the algorithm has created is right or wrong. For that, the second part, from the multiple sequence alignment. Now here you can see this is multiple sequence alignment. Already we have constructed. Based upon this, we have to go for a distance based method. So that is neighbor joining method. You know, there are three different distance based methods. One is UPGMA unweighted pair group method with arithmetic mean. This is one distance based method. Another one is Fitch-Margoliouth, and third one is neighbor joining. Neighbor joining method is the most popularly exploited method for predicting phylogenetic analysis. So what we are doing from the constructed multiple sequence alignment, that is from this multiple sequence alignment, I will build a distance table. From the distance table, I will apply neighbor joining method, which predicts an unrooted tree as well as where the branch length in the unrooted tree is also unequal, right? So that is the speciality of NJ method. So we will use NJ method and we will predict a phylogenetic tree. Now the results of phylogenetic tree should be equal, or it should be exactly similar to that of this initially constructed multiple sequence alignment, right? So first one is use dynamic programming method. You construct a multiple sequence. Second, from the multiple sequence alignment, you construct a phylogenetic tree and you compare the results of phylogenetic tree with the results of initially constructed multiple sequence using dynamic program. Both the results, if both the results are concordant, both the results are exactly same, then automatically the results will be protected. Now it's okay. If there is a discrepancy, then you believe the result which was generated by NJ method. That's what it says. Align sequences sequentially according to the result guided by the phylogenetic tree. So second step is very, very important, right? So very simple. Construct multiple sequence alignment using a dynamic program method, right? From that, the second part, build a phylogenetic tree using neighbor joining method. You observe, you compare the results generated by phylogenetic tree with that of initially generated multiple sequence using dynamic program. If both results are same, then the results can be published. If there is a discrepancy, you refine the results according to the prediction of the tree, right? Now we will go for a simple practical demo. So here, very simple. We'll go for just you type EBI. You can enter into European Bioinformatics Institute. So here, what you have to do, you have to click services. Now, the first itself, you can see CLUSTAL Omega, right? So use this particular tool. This is the enhanced tool hosted by European Bioinformatics Institute, mainly to align protein sequences or DNA sequences in multiple. So go for this, right? Now you can see over here. Now we want to have sequences. So where to take sequences? So go to NCBI, go to straight away protein. Now here we'll take a simple polypeptide which contains less number of characters. So we will use insulin. Now at least it's a multiple sequence alignment. So how many number of sequences is mandatory? N is equal to 3. Minimum 3 sequences you have to put. This is not pairwise. So we will select serial number 2, serial number 3, serial number 5, serial number 6, serial number 7. So for this, we will get the FASTA sequence. Get the FASTA sequence, and if you want, even you can download the FASTA sequence over here, right? So now for time being, so we'll go for the we'll paste the sequence, or even we can, if you want, we can download, no issues. If you want, you can download over here. So now it is here, right? So we'll take the, we'll upload the sequence. So we will upload. So here I have downloaded, I have kept in my desktop. So I can choose a file over here. So in the desktop, you can see MSA, that is multiple sequence alignment. So just I have uploaded in the FASTA format, you can see. Now there is, we are not going to touch, we are not going to optimize anything. We will leave the defaults as such. So submit. Patiently you wait, it will refresh, because total number of sequences, hope we got 6 years. Now here you can see, right, different thing. Now the speciality is, now this is in black and white. It could be difficult. Now here you can see some symbolic representation. Gaps will be represented as hyphen marks, and here you see the conserved characters will be represented by asterisk, and the accepted mutations will be denoted by colon marks. So here you can see D and E. So E is glutamate, D is aspartate. Both are acidic amino acids. Instead of aspartate D, if you are going to replace with E glutamate, there will not be any structural and functional loss to a protein. So that was indicated by colon mark. That means acceptable mutation. This you can take into account for similarity. Whereas the single dot, again, you can see this is unacceptable. That means that there is a big negative effect. Say valid, is highly hydrophobic, aliphatic, branched chain amino acid. When you're going to replace with the T, which is a methylene hydroxy amino acid, 309, 309 is polar. It contains methylene hydroxy group, which can form hydrogen bond. So the from polarity wise and molecular weight wise, it is also unbranched. T is unbranched. The properties are totally different. So when you replace valine with the 309, there will be a structural loss and functional loss to a protein. So that is lethal. It is unacceptable mutation. This should not be counted for similarity, which was indicated by a dot. So this is the description for this asterisk or colon mark or single dot. Now the result is not pretty, so you can make your result in a very pretty way. You can ask to show us colors, right? So now here you can see. So now pretty, it is in color. Now you can see, right? So what I have projected early in my PowerPoint presentation, right? So now here you can see, right? L and V, E is different, right? Now you want to download, right? So you can download your alignment file. If you want to construct a phylogenetic tree, you can also construct, just to construct, no issues. So here you can see, and the cladogram based phylogenetic tree is not good. You can see branch length is uniform. That is not right. So we'll go for a phylogram, which is real. Now here you can see the branch length is a little bit, say, you can see it is unequal. So here the branch length is unequal. So this branch, the length of this branch is greater than this particular branch. So even though both are similar, this particular species would have arose little bit later than this particular species. Whereas when you go for a cladogram, you can see the branch length seems to be equal, which tells you that these two species arose at the same time, which is totally impossible. Right now, here you can see. So if you want to construct, you can construct over here, and this is Nevick's formula. So it is here. So now this is apart from our lecture. So we'll go for very simple alignments, and then we will download the alignments, right? So you can save in the desktop, right? So we'll save. So next is we want to find the conserved characters. So we can go for BOXSHADE, right? So we type BOXSHADE. You can go to this particular server. So open the BOXSHADE, right? So now everything is ready, but we want to upload the file in an acceptable way for this particular BOXSHADE server, right? So what we will do is very simple. We will convert the downloaded alignment file, right? We will convert the downloaded file. We will convert the downloaded file into a notepad. Right? So yes. So just you right click and you select notepad. That's all. That's what I'm doing over here. So again, once again, we will download this. So yes, yeah. Shared in the desktop. Yes. So I have effectively converted. Very simple. So now go to this, you select this option, you go for rich text format new, right? Then here you go for line, right? Now you paste the format over here. Now this is what I have converted the notepad. So you paste it, and run BOXSHADE. Now output is given. You can download the output. You can see that output was downloaded as a rich text format. You can open, right? Now here you can see, fantastic. Now I have successfully converted the same result. Now you can see the result. What you have observed over here is almost same. So here, what you can do, even you can show in colors, right? That's all. But the conserved characters was not highlighted, right? Whereas here, the conserved characters was highlighted. Right? Now here you can see Q, 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 Q. The conserved characters was totally out. So I will share. So here you can see. So this is what the even show the box say. So it will look like this. Yes, now here you can see. So it was like this. So pretty, we can visualize the sequences through multiple, through different colors. And in order to find the conserved characters, use BOXSHADE. The output from CLUSTAL Omega can be uploaded into BOXSHADE server, and you can find what sequences are highly conserved. Right? So friends, hope you got an idea about multiple sequence alignment. Today I have dealt only CLUSTAL W due to lack of time. So in my sequence of lectures, I will try to cover other alignments. So thank you. Thanks a lot. If you have any worries, you can mail to me at satishkumar.t.bt@kct.ac.in. SATHISHKUMAR dot T for tiger dot BT technology at kct.ac.in. So any queries, I'll try my level best to answer.